Hi everyone. Today we are going to go through what a free body diagram is in the topic of forces. We use free body diagram, in short we will call it FBD, because we want to represent forces acting on an object. And in physics, one way of simplifying a complex scenario is to treat each object independently and do our analysis on them. Hence, the word free body means that we are only focusing on one and only one object. To represent the object in a FBD, we use simple shapes such as a square or a circle. Take note, in a FBD, only one object should be drawn. Next, let's look at how we can represent the forces acting on this object. A force, like you have learned, is basically a vector quantity. In a vector quantity, the length of the arrow represents how strong the force is. The arrow also tells us the direction of the force. This is an example of how a force vector is drawn using a ruler. So over here, you see a force vector that is pointing towards the right. This tells us the force is acting towards the right, and the length of the arrow tells us relatively how strong the force is. The start of the arrow, as shown by the dot, tells us the point of application of the force, which in other words tells us where the force is acting on. We should also properly label the force by putting a F over here. For example, in this case, let this force be a pushing force. We should also indicate which object exerts this force on this particular object by labeling the subscripts as such. Let us now see how a FBD of a box resting on the floor will look like. Over here, I have drawn a very simple square to represent the box. Let us first draw the weight of the box. I will first create a legend at the side to indicate W stands for the weight acting on the box. Now, weight acts on every single particle of the box. So, if we were to draw a very accurate diagram, we will have to draw literally 1,000,001 arrows that represent the weight of the box. Now, this isn't the most feasible way of doing a free body diagram. Therefore, let us simplify the whole process of representing weights on a box. So, where should we draw just one downwards arrow to represent the weight acting on the box? The answer is very simple. Let us just take the geometrical center of the object, for example, here, to show and represent where weight acts on the box. So, using a ruler, let us now construct a downwards arrow to indicate the weights of the box. Again, let me emphasize, this doesn't mean that weight only acts on the center particle of the box. Weight acts on every particle in the box, and this is just one way of simplifying the 1,000,001 arrows that we'll have to draw otherwise. So, with this weight arrow drawn, let us not forget about the subscripts to indicate the objects involved in this gravitational force. So, weight is caused by the earth acting on the box, and that is an example of one properly labeled force vector. Now, the box is supported by the ground, otherwise the box would have fallen into the ground. This supporting force is what we call a normal contact force. Let's label this normal contact force in our legend. So again, this normal contact force supports every single particle at the bottom of the box, and we would have to draw many arrows to represent this normal contact force. Let us simplify this process. Instead of drawing so many arrows, we will again take the average and start the arrow from the center of the box at the bottom surface of the box. Using a ruler, let us construct an arrow that is approximately the same length as the weight and we will label it N, the normal contact force. This force is caused by the ground acting on the box. So this would therefore be a properly labeled free body diagram of a box resting on the ground. Let us look at one more example of a box being pushed by Chris and being pulled by Pamela. Again, I will draw a simple box to represent the box on the ground. Over here, we have seen the box being drawn with the weight of the box and the normal contact force acting on the box being labeled properly. Next, there should be a pushing force by Chris acting on the box. Let us draw that in. And this force is exerted by Chris acting on the box. Now, if you look at the right side of the box, we would notice there's a force being acted on the box at this dot right over here. Now, what is in contact with the box? We will see that a rope is in contact with this side of the box. Therefore, we shall now draw an arrow indicating the force acting by the rope on the box. The moment we see a force being acted by a rope or a string, let us label the force as T, where T stands for tension. We are almost done with this FBD. This box will have the tendency to move towards the right. So, as we all know about friction, frictional force opposes the tendency to start moving, or frictional force opposes motion. Since the box will tend to move towards the right, we shall represent frictional force in this way. With a small f exerted by the ground on the box. Let us complete the legend by indicating what F stands for, frictional force. And there you go. This is a free body diagram of a box that is pushed by Chris and pulled by Pam.